If Alice, Betty, and Chase are interested in a position in the math club, and you need to choose two of them to be the president and vice president of the math club, how many ways are there to do this? So we're going to solve this in two methods. The first method is just to list them all out. So if Alice is the president, then Betty can be the vice president, or if Alice is the president, Chase can be the vice president. Similarly, if Betty is the president, we can either have Alice be the president or Chase be the president. And you can have somebody be both the vice president and vice president, right? And then similarly, if Chase is the president, either Alice or Betty can be the vice president. So there are a total of 6 ways. And this worked fine because we had small numbers. But what if we had large numbers? So now we're going to explore a more clever way to solve these types of problems. So now let's just say we have A, B, and C. Okay, so now we have A, B, and C. How many choices do you have for the president? The president can either be A, B, or C. It can be any one of those 3 people. So 3 choices for who gets to be the president, right? And now let's just say the president was A. So A can't be the vice president anymore, since nobody can be the president and vice president. So now that A is gone, A can't be the vice president. Only B and C are left to be the vice president. So there are 2 choices for who gets to be the vice president. So overall, there are a total of 6 ways, since 3 choices for the president and 2 choices for the vice president. Because after somebody's already the president, there are only going to be 2 people left to be the vice president. Any questions on this problem? And yeah, we can just think of another way to think of it as slots. So this would be the president. And then this would be the vice president. So we can think of it as 2 slots, the president's slot and the vice president's slot. And you're saying, can you just do factorials? You're saying, okay, A, B, and C, we're lining them up. Yeah, that's something that you can do. This time we're only choosing 2 people, then we just order 12 people. But if you have just like Justin said, you can have 12 people, A, B, C, D, F, G. Now let's say you want 2 people from these people, then you can't do factorials anymore. And there's actually a formula for choosing and permutations and some more complicated stuff that can come on the AMCA. And I'll link that video so you guys can all see it. So there's a more complicated video about combinatorics with factorials, permutations, combinations, and I'll send you that video if you're interested. But for now, for this class, we're only going to be focusing on these 2 main techniques. So we're not going to worry about that for this class. So okay, let's move on to some problems now. 5 people are introduced to each other, and each person shakes hands with each of the other exactly once. How many handshakes are exchanged? So let's just say the 5 people are 1, 2, 3, 4, and 5. The 5 people, we can just number them. Okay, so for each person, so 1 can shake hands with 2, 3, 4, or 5. Two can now shake hands with 1, 3, 4, or 5. 3 can now shake hands with 2, 1, 4, or 5. And now it's getting a little bit confusing, so I'm now going to erase that. So I'm just marking. And then similarly, you can have 4 shakes hands with 1, 2, 3, and 5, and 5 will shake hands with 1, 2, 3, and 4. I'm not going to mark it because that will be confusing. Okay, so we see that for each of the 5 people, so for each one of these 5 people, they shake hands with the 4 other people. Except there's one thing that we may not have here. In a handshake, 1 handshakes with 2, and 2 handshakes with 1, but these are the same thing. It's still 1 handshake. 1 handshake is being shared by 2 people. And this idea is a little bit confusing, so let me explain. So remember when we counted 1 shakes hands with 2, and then 1 shakes hands with 3? But then when we counted also, we counted 2 shakes hands with 1, and 2 shakes hands with 3. And then for 3, we counted 3 shakes hands with 1. And we see that for each handshake, we're counting it twice. Because 1 is shaking hands with 3, we're counting when 1 shakes hands with 3. We're also counting when 3 shakes hands with 1. But really, it's the same handshake. They're not 2 different handshakes, 1 to 3, 3 to 1. The handshake is mutual. So we're overcounting, so we have to divide by 2 for this case. The reason for this, again, when you're exchanging 2 handshakes, rather than just counting from one person to the other, you're counting the opposite. So that's why you divide by 2 to get 10. Any questions on this method? And now I'm actually going to explain another method. And this method is that 1 will shake hands with 2, 1 will shake hands with 3, 1 with 4, and 1 with 5. So that's just 4 ways. And now 2, and this is like a different kind of approach. 2, it will not shake hands with 1 anymore since we already shook hands with 1. Instead, it will only shake hands. The only new handshakes are 2 with 3, 2 with 4, 2 with 5. So that's plus 3. And then let me erase that now. Now for 3 already shook hands with 2 and 1. We already counted those handshakes. So now 3 shakes hands with 4, 3 shakes hands with 5, that's 2 more. And now 4 shakes hands with 5, so that's plus 1, and we get 10. Again. Any questions on the second method? Okay, let's move on to number 2. When the order of the digits of 2552 is reversed, the number remains the same. So if you remember from last class, these types of numbers are known as palindromes. So what this means is, so let me give an example. I think I explained this last class. So 393 reads 393 forward, but if you read it backward, so if you go the opposite way, 393 is still 393. And for some bigger one, 1 2 3 2 1, for example, it reads forward 1 2 3 2 1, and backward it reads 1 2 3 2 1. And this is known as a palindrome. And now we're asked to find how many numbers between 100 and 1000 remain in the same order. The numbers digits are reversed, or essentially how many of them are palindromes. Okay, so from 100, we can have 100, 101, 102, 999, 1000. So we really see that this is really just the 3-digit numbers plus 1000. And 1000 is not a palindrome, right? Because if we read it backwards, it's 0001. And 0001 is not the same as 1000. So 1000 doesn't work. So now really all we have to find is the number of 3-digit numbers that are palindromes. So from 100 to 999. And if you remember from last class, we did something again similar. It's going to be in the form ABA. Because in order for it to be a palindrome, the first and third digits have to be the same. And the second digit, well, it can be anything, since it will be the same position when you read it forward and backward. So like 121, 191, the second digit doesn't matter because 121 and 121 read the same way, and 191 and 191 read the same too. So the second digit can be anything except the first and the last digit. The first and the third digit have to be the same. So now we know how many numbers of the form ABA are palindromes. Okay. So let's try to figure out. So what can A be? A can be from 1 to 9. It can't be 0. Because let's just say that A was 0. If A was 0, then it would be like 030, let's just say. And 030 is not a 3-digit number. So we're just asked to find how many palindromes are there from 100 to 999. So 030, for example, won't work 0 to 0 won't work because when it's not a 3, it's less than 100. 100 is greater than it. So essentially the problem is just asking, it reads the same forward and backward. So as I explained here, and I also explained it last class, so you can review the recording from that. I explained like the concept of palindromes last class. Yeah, you should, there's a video explaining more about, I explained more about it last class. Okay, so now that we have from 1 to 9, and B can be from 0 to 9. Okay. So A can be anything. So A can be anything from 1 to 9. So there's 9 choices. Yeah, we have to find the number of palindromes from 100 to 999. And B can have 10 choices. And okay, let me explain. So A has 9 choices. B can be anything from 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 choices because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. And but then 1 through 9, it has to be the same as A. So there's only one choice, right? Because A has to be the same as A. So if we choose A to be 3 and let's say B to be 6, then A has to be 3, again, the last digit. So the answer is 90. Any questions? Let's move on now. A boy has the following 7 coins in his pockets: 2 pennies, 2 nickels, 2 dimes, and 1 quarter. He takes out 2 coins, records the sum of their values, then puts it back with the other coins. So he has these coins here, and he takes out 2 of them, and he's finding the sum of them, and then he's putting it back. So he takes out 2 coins, and he's asking for how many different sums there can be. Okay. So we have 2 pennies, 2 1 cents, so 2 1s, 2 5s, 2 10s. So I'll just make it clear: 2 5s, 2 1s, and 1 25. So now we have this strange 125 here. What do we do with that? 1 quarter. What? Let's just do some cases here. So let's just think that we include 25. So the first case is we have 25. We include it. It's 25-cent coin. So now we have the 25. Now we have to choose one more coin amongst the 2 1s, the 2 5s, the 2 10s. We have to choose. We already have a 25. We're choosing 25. That's part of our case. And now we have to choose another coin. So how many different ways are there to choose another coin? Well, we either choose a 1 coin, a 5 coin, or a 10 coin. So you can only take a 1, 5, or a 10 coin, because there really is only 3 possibilities. You can only choose 1 coin, so you can't have 2 1. You can only choose 1. So really, there's only 3 types of coins that we can choose. So really, we have to take a 25 plus a 1, a 5, or a 10. So there's 3 ways here. And the second case is a little bit more tricky. Not include 25. We don't include it. So now we have to choose 2 coins amongst the 2 1s, the 2 5s, and the 2 10s. Now instead of just choosing 1 coin, we have to choose 2 coins. Okay, so what are the possibilities? We can either take a 1 and a 1. We can take a 1 and a 5. We can take a 1 and a 10. Or we can take a 5 and a 5, a 5 and a 10, or a 10 and a 10. So hopefully this is clear. So we can always choose 2 coins. So we can choose 1 1, 1 5, 1 10, 5 1, but we already counted that here, so we won't include that since we already said 5 1 was counted. And then 10, 10, we already included the 10 with the other coins, so we really only have 10 with itself. So there's 6 possibilities. The total is just 6 plus 3 or 9. Any questions? Okay, let's move on to the next problem. A total of 15 pennies are put into 4 piles, so that each pile is different number of pennies. What is the smallest number of pennies that can be in the largest pile? So 15 divided by 4. So before I even begin, so we have these 15 pennies, so we have 4 piles. Let's just say that we order them. Let's make them from least to greatest. So least from greatest. So now we can only really have from least to greatest. So now we're just ordering them from least to greatest. We're ordering them to 4 piles. We want to look at the last pile at the end. Okay, so what's the average number of coins in each pile? We have 15 pennies in 4 piles. And that means there's 3.75 pennies on average. So since there are 3.75 pennies on average, the largest number of pennies has to be at least 4 or more. Like it cannot be any less than 4. Since if the average is 3.75, the largest value has to be greater than the average value. So the largest value has to be at least 4, no more. Okay, so now we know the largest value has to be at least 4. So is it possible for 4? Well, if it's 4, then we have to have all different. So for the next value, this next largest value can be at most 3. The second value can be at most 2, and that means the first value can be at most 1. But that means the sum is only 10, even in the best case from 4. Right? Because you have to have all piles must have a different number of pennies. Different number of pennies in each pile. So even if you just take 1 down from the largest, we only have a sum of 10. That's too small. That's too small. So this doesn't work. Okay, now what if we have 5 here? What if we have 5 here? Okay, then this value has to be 4 at max. Remember, because the second largest value cannot be the same as the largest value, but we're trying to make it as big as possible. So let's just make it just a little bit less than 5, so 4. And the second value can be 3, and the first value can be 2. And what is the sum now? If you add it up, we get that it's not enough still. It's 14, just 1 below. So even in the 5 case, if you want to have them all different, 5 is still too small. 5 doesn't work. So that leads us to check 6. So for 6, let's just say this is 6. In the best case, this would be 5, right? And there's actually 6 is actually the correct answer. 6 is the answer. I'll explain why in a moment. So there's actually many ways. So we can have maybe like 6, 5, and then if we can have like 3 and 1, then that would work. There's many different ways because this has a sum of 14. But there's actually several more. So we can have, if you think about it, like the intuitive way to think about this is if this is 4, now we're exactly at 15. And that's good. We are at a sum of 15. Should be, yeah, not 15. That should have been 15, not 14, sorry. Okay, so now 4 plus 5 plus 6 is 15. But we want 4 values. So we can just maybe split the 4 into a 3 and a 1. So we can make it 3 and a 1. Because now we know we can split the 4 up into a 3 and a 1. But there are actually some other ways. So now we know that 6 is possible. So that's our answer. But there are actually some other ways that do work with 6, and I just want to illustrate this to make it a little bit more clear. And if you see here that we can, another way to intuitively think about this is that this was just 1 off. Like it doesn't work for 5, but maybe if you just increase it by 1, we just need 1 more, just 1 more, that's it. So if we make this a 6, then we can keep all the other values the same. We can keep them 4, 3, 2. And now it's going to be 15 because we just increased this by 1 by making it a 6 instead. And those are the other ways I showed earlier. So there are actually several other ways, but I won't show them. Well, from here we can see that the answer is 6. Any questions? So let's move on. How many unordered pairs of positive whole numbers sum to 43? So let's just write out a few to get the hang of it. So 1 and 42, 1 plus 42 is 43, right? Those are both positive numbers. Maybe like 2 and 41 is 43. Also, 3 and 40 give 43. 4 and 39 give 43. 5 and 38 give 43. So on. But when do we stop? So let's just see. And then we can keep writing 6 plus 37, 7 plus 36, so on. We can keep writing. Maybe then we'll get to 21 plus 22. We have 21 plus 22 is 43. So you have 21 plus 22 is 43. So now we see that this is indeed is a possibility. But then if you go even further, let's see we have 22 plus 21 is also 43. But then we see these are the same. These are the same thing. There's nothing different about them. Because unordered pairs of positive whole numbers. So having 21 and 22 is the same as having 22 and 21, since they have to be unordered. So this doesn't work. So at most we can only have we can see that there's only can be from 1, 2, 3, 4, 5, all the way till 21. Only 21 at max. So 21 is the answer. And the reason for this is we can have from 1 to 42, 2 to 41, 3 and 40, 4 and 39, 5 and 38, till 21 and 22. We can't go any further than that. Because then now we have repeats. So basically the idea is we keep going while the second number is larger than the first number. Since after the first number becomes larger than the second number, then it's the same thing, just in a different order. So then we can see there's only 21, since we're just going from 1, 2, 3, 4, 5 till 21, which is 21. So there's 21 possibilities that work. Any questions? Okay, let's move on. Peter has one of each of the following coins in his pocket: a penny, a nickel, a dime, and a quarter. So a 1-cent coin, a 5-cent coin, a 10-cent coin, and a 25-cent coin. And he had to choose 3 of them. 3 of these coins are taken out of his pocket, and the sum of the values is calculated. Okay, so he's taking 3 of them. So we have 4 coins, and he's taking 3 of them. So how many ways are there to do that? So here's a hint here. So there's 3 coins, and we're trying to take out 3 of these 4 coins. So how many different sums? So actually try to solve this on your own. So here's a big hint here. In order to choose 3 of the coins, we can choose 4 of them and then remove 1 coin. So try using that as a hint. And try solving it then. And you can private message your answer if you get it. So now I'm going to continue a little bit, since some of you have got the answer now. So the sum of the coins, if you just take all of them, so we have to take 3 of them, choose 3 of them. So now let's imagine taking all 4 and then choosing 1 to remove. So the sum of all 4 coins is 41. So if you take all 4 coins, we have 41 cents. But we only want 3 coins. So now how many ways is there to subtract 1 coin? We have 4 coins, we want 3 coins, we subtract 1 coin. So we can really subtract any one of the 4 coins. We can subtract any one. We can subtract the penny, we can subtract the nickel, we can subtract the dime, or the quarter. So there are 4 ways. Because we can choose all the 4 coins, we can take all the 4 coins, and then choose one of them to subtract off from our total. Since we have too much. We have 1 more than we should have. Any questions? And okay, since we have enough time for today, I'll also just list out the options that we have. You can either take a penny, a nickel, and a dime. You can take a penny, a nickel, and a quarter. You can also take a penny, a dime, and a quarter. Or we can take a nickel, a dime, and a quarter. So there's 4 here too. But then it's actually easier to do it the first way, but this is just to demonstrate to see what 4 possibilities of coins you can actually choose. Let's move on. So now this is going to be one of the more slick methods. Unlike the other problems, we can't just list out all the possibilities. We're gonna have to use a slots method. How many 4-digit numbers can be formed using the digits 0, 1, and 2? So what can we do first? Let's look at the possibilities for each digit. So they can be 0, 1, or 2. So what are the possibilities for the first digit? What are the possible options for the first digit? 1 and 2, yes. And the reason for this is we can have 0, 1, or 2, but we can't have 0, since if you have something like 0, 3, 8, 8, this is not a 4-digit number. It's a 3-digit number because the 0 isn't there. So the first digit can be anything we're allowed to have but 0. It can't be 0. So it can be 0, 1, or 2 except 0. So it doesn't work. What about for the second digit? What can we have? For the second digit, what are the possibilities really? So we have the possible options of 0, 0, 1, and 2. Yeah, so correct, that's correct. So some of you said it that the possible options are 0, 1, and 2. And in this case, we can have 0. 0 is allowed. Having 3, 0, 8, 8 is allowed. We're allowed to have this. This is allowed. So we can have, but then even having 1, 3, 1, 8, 8, for example, would also be fine. So these 0 can be in the second or third or fourth digit. It just can't be in the first digit. Since it was in the first digit, then it would no longer be a 4-digit number. And similarly for the next 2 digits, it's also 0, 1, and 2. Right? Because it can be anything. It can be 0 if it can. So now what? So now there are going to be 2 choices for this digit, since 1 or 2. 3 choices, 0, 1, or 2. 3 choices, 0, 1, or 2. And 3 choices, again 0, 1, or 2. This is 2 times 27, which is 54. And listing that out would be very hard, so I don't recommend it. An example of a number, let's just say we took 1 here. You could take maybe a 0 here, maybe another 0 here, and maybe a 2 here. So 1002 would be a 4-digit number with 0, 1, and 2. Any questions on this trick or type of problem? Because this is very important. It's one of those crucial ideas, so make sure you understand how this method works. Okay, let's move on then. So this is another kind of clever problem. So I'll explain it in more detail. So Abracadabra has 4 different coins with values of 1, 2, 4, or 8. Suppose you had just one of each of the 4 coins. So you only had one. So you had 1, 1, 1, 2, 1, 4, and 1, 8. So what are the possibilities? So I'm gonna do this 2 ways. I'm gonna first do the more intuitive way. So suppose you just had one, how many different amounts? So let's just do some cases. Let's just say we only had 1 coin. Oops, 1 coin. If you only had 1 coin, well, we can only have 1, 2, 4, or 8, right? We have to have 1 or more. We can't have 0. If there's 2 coins, we can have 1 plus 2, 1 plus 4, 1 plus 8, 2 plus 4, and 2 plus 8. And then we can also have 4 plus 8. This is just 3, 5, 9, 6, 10, 12. Now what if you have 3 coins, 3 whole coins? And actually, I'm going to again use some kind of a logic. I'll do 4 coins first, actually. I'll do the case for 4 coins first. So if you have all 4 coins, we have to have 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8. Actually, let me make that a little bit more clear on the left side. So you have to have 1 plus 2 plus 4 plus 8, which is 15. If you have all 4 coins, there's only one way, right? You have to have 15. There's no other possibility. And for 3 coins, again, just like if you remember from the number 6, we thought of maybe having all the coins and then choosing one not to have. So for the 3 coin case, let's say we had all the coins. Now say we don't want one of them to be the coin. So having all the coins, so if you had all the coins, it's 15. But the possibility is when we don't have one of the coins. So to get 3 coins, we have to have all 4 coins except 1 coin. So 15 minus 1, 15 minus 2, 15 minus 4, 15 minus 8, which is 14, 13, 11, and 7. And now let's see what numbers we have. We have 1, we have a 2, we have a 3, we have a 4, we have a 5, we have a 6, we have a 7, we have an 8, we have a 9, 9 is here, we have a 10, it's right here, we have an 11, which is right here, we have 12, which is right over here, we have a 13, which is here, we have a 14, which is here, and finally we have a 15. And is it a coincidence that we have all the numbers? Okay, so from here we can immediately see the answer is 15. Since we have 15, we can make any amount from 1 to 15. So 15 is your answer. But the reason instead of listing them all out, instead of just counting the number of numbers, is that there's actually a big coincidence here. We have all the numbers from 1 to 15. That might seem strange. So the reason for this is, so how many of you have heard of a binary representation of numbers? Have any of you heard of a binary representation of any numbers? So that's basically what it means is, I'm not going to explain it into the terms of the base. So 15 can be expressed as the sum of powers of 2. So it can be expressed as 8. It can be expressed as 8 plus 4 plus 2 plus 1. And written in binary rotation, this is just 1, 1, 1, 1. And don't worry about this too much. Just focus on this representation. And maybe like 11 is 8 plus, there's no 4, but there's a 2 and a 1. So we have the 8 and the 2 and a 1. And then let's say a 12 can be expressed as 8 plus 4, but there's no 2. I'm not sure what happened, but let's continue. So we left off at 12. 12 is 8 plus 4 plus we don't know what these two values are. And we can see that even with some other numbers like 13 is 8 plus 5 or 8 plus 4 plus blank 2. There's no 2 plus 1. And every number has a binary representation. It can be expressed as a sum of powers of 2. And we're given here that we have 1, 2, 4, and 8. So we can either choose to have a 1, a 2, a 4, or an 8. You can choose to have them. So therefore, we can express any number 1 to 15 as a sum of some of these numbers. And that's because of the binary representation. And don't worry about it too much. Just remember that this kind of casework is probably the right idea. But this is just a cool trick, cool fact here, is that any number from 1 to 15 can be expressed because it's binary. Be expressed in terms of binary. Every number has only one binary representation. That's the good part. There's no way to write it as 11. You can't write it as sum of maybe 4. There's only one way to express it. That's the uniqueness of this binary representation. So let's move on to the next problem then. Or before are there any questions? Let's move on. Okay, 6 people participated in a checker tournament. Each participant played exactly 3 games with each of the other participants. How many games are played in all? So try solving this on your own. So here's some hints. 1, 2, 3, 4, 5, 6. And each participant plays 3 games. So how can we do this problem? So try it on your own, and I'll give a hint after some time. Here's a hint. So basically what this is we have 6 people. And if you remember from earlier, we can think of them as 6 people. We choose some number of people. I won't give it away right now. And then each game is counted some number of times. So you divide by something. And then you multiply by something at the end. And I don't want to give too much away right now. I'll get a little bit more of a hint later. But the key idea is look at the number of people, see the possible choices for who gets to play which game. So number of choices for the game that's going to be played with each other team. So that's a minor hint here. So this is like the answer form. What is your final expression? Let me explain now. So there are 6 people to choose for who's playing the game. So for each of the people, they play a game with each of the other 5 people, right? With either of we also can connect them. So for each of the 6 people, we can always play a game with the other 5 people. So 6 people we're playing with, and each of them plays a game with 5 other people. So for each of the 6 people, they play 5 other people. But if you remember from the handshake problem, the first problem, it was we were doing 5 handshakes. When 1 plays a game with 2, it's the same as playing when 2 plays a game with 1. And we're counting these twice. We're counting them twice. And if you want more reference, we discussed this in the very first problem. So feel free to refer to that later. So we discussed how having 1 with 2, playing 1 with 2, and then when we count 2 with 1, it's the same thing. So we're counting each game actually twice. So we divide by 2. But then this is actually one thing that you should be really, really, really careful of. Each participant played exactly 3 games. 3. Make sure you don't mess this. This is like a very key information. So actually, it's going to be times 3 here. Because each of the people play games with 5 other people 3 times. So they play it with it 3 times. So make sure to not miss this piece of information. So instead of just having 6 times 5 divided by 2, there are 6 people. Each of them plays games with 5 other people. And they play 3 games with each of those 5 other teams. And that's why it's just going to be 6 times 5, which is 30. 30 times 3 is 90. And 90 divided by 2 is 45. And now since we have enough time, I will also explain the other method to this problem. There's another method to this problem. And yeah, like I said, it was 6 times 5 times something divided by the something. That's the formula of the answer. And I'll explain it the other kind of slightly different way that we did. So one plays with 2, 1 plays with 3, 1 plays with 4, 1 plays with 5, and 6. Right? And then 2 plays with 3, 2 plays with 4, 2 plays with 5, 2 plays with 6. But we don't count when 2 plays with 1 because we already counted that. We're only counting the games that were not played with 1, since we already counted all the games played with 1. So then we already have 6 plus 5 plus, and then, okay, then 3 will play with, 3 can play with 4, 3 can play with 5, with 6. And then we don't count the ones played with 2 and 1. That's plus 4, plus 3, plus 2, so on. And then finally, 5 already played all the games with 1 through 4, so it has to play a game with 6. So it's plus 1. And you can just add this up. There's actually a quicker way of doing this, but you add up, you get 15. Sorry, yeah, it should not be that. It should be 5 plus 4 plus 3 plus 2 plus 1. I don't know why I included a 6 there. It should be 5 because the person 1 plays with 5 other people first, not 6 other people. And then it keeps reducing. 2 plays with 3, 4, 5, and 6, but it doesn't play with 1 since we already counted that. So it's 5 plus 4 plus 3 plus 2 plus 1, which is 15. And then again, we're forgetting to multiply by 3. there's 3 games. Each participant plays 3 games. So we have to do 15 times 3. Because instead of just playing with 5 other people, but there's a times 3 term here. Because we're playing 3 games with each of those things, with each of those other teams. And this is just going to be 15 times 3 or 45. Any questions? Let's move on to the last problem. This is probably one of the more tricky problems. In a 2x2 grid, how many ways are there to go from the bottom left to the top right vertex? Okay, so how many ways are there to do this? So I drew out some grids here. I kind of gave away the answer, but don't worry about those grids. So I'm actually going to explain this problem in 2 ways. One is we just write them all out, and one is a smart way, which I'm going to do over here. So let's first explore this is the more intuitive way, just listing them all out. And so the first key observation here is that we have to take a path. Will have to be the minimum distance of a path is 4, because we have to go from here to here. Or let me just explain the same diagram. We have to go from here. Oops. You have to go from here to here, and we have to go take 2 up steps, and 2 right steps and 2 up steps, for a total of 4 steps. So an example of I'll just draw on the second grade for now. And an example of a smaller, so let's just say we took a bigger path. So actually, let me make it a little bit more clear. I think it's a bit unclear. So I'm going to draw, let's just say we have something else, maybe took like a detour. We went, instead of just going up and right, we took maybe a down. Maybe instead of taking up and right, we just went down. So the question should actually state with the shortest path. The shortest path. The question should say that with shortest path. How many ways are there to go from the bottom left to the top right? So if we go by this, path, if we take a detour and then we go up and then we go up, this is not the shortest path, since now we took 1, 2, 3, 4, 5, 6. We took 6 steps. So that's not going to be the shortest path, because now we're countering, instead of just going all up and right. So if this was not clear, I'll just draw it with some other color. So maybe like that. You have this kind of a long path. And then we take another one. So you're taking some kind of a detour path. We're not going straight up. Now we're taking an up step. We're counting an up step. Now we're also going down. We're going down again. But then we're kind of canceling our steps. We're adding extra steps. So the shortest possible path is when you just take only up, only right. Because we're really trying to go up and right. And if you add any lefts or downs and everything, we need more to make it up for it. So if you go down, you have to add another extra up. So this would be a total of 6, because we wasted 2 steps by going up and going down. So that's the reason we have to go up and right in order to get the shortest possible path. So is this clear to anyone? Does anyone have questions why we always have to go 2 up and 2 right to get the shortest possible path? Okay, so it looks like it's clear. So now I'm going to do it the first method. This is actually a really tricky idea, so I'll just try to explain it. So we're going to do a little bit of casework here. So we're going to look at 2 possibilities. What if we just take a right step? So we have to take only right and up steps. So what if our first step is always a right step? Then now we do casework. So first step is a right step. So now what are the possibilities? we can either take an up step. From here, we can either take an up step or we can take a right step. So the second step can actually either be up or right. I'll just write those two possibilities. But then let's just say we took a right step. Now we're already at the corner. We already used all our up and right steps. Now we have to just go up, straight up. So in this case, we just have to go straight up. That's it. That's our only possibility. Nothing else. Okay. So that's just one way to do that. So there's just one way here. But now what if we go up and then right? If you go up and then right, well, now we can either go another up or we can go right. So let me write the same here. So if you go up and then right, we can either go up or right. So we can go up or we can go right. And then from there, there's only one way to finish it off, right? So we can only go like that or like that. So you either take a right step, then up step, or up step, then a right step. So each of these adds one way. And then we can do something very similar. So I'll just draw the same thing. These are three ways. These are three ways, as you can see. So now the other cases, let's just say you're starting here. Now let's say you take a up step first. So if you take a up step first, now again, let's divide it into some cases. Let's just say we take an up step for all these three cases. And you don't know it's three, but I'll just draw it for now. So let's just say we take it for one case. Now the second step can either be up or right again. So this can be either up or it can be right. Or it can be right for these two. And if you go an up step after that, now there's only one way, since we have to go right and then right, because we have to go straight to our destination. Make it a little bit. And then now let's say we have these two positions. So we have these two positions. So now from this position, we can either take an up step or a right step. We don't know. And then in each of these cases, after that, we just go, let me make it. And after that, we just have to go take a step. There's nothing we can do. We just go straight to our destination, because we can only take up and right steps in order for the shortest possible path. And as you can see here, there are 6 ways. Oops. 6 ways. So I think it was a little bit unclear because it was a thin pen. Oops. I'm just going to make it a little bit bigger so it's easier for you to see, and make sure to see what the actual path is. So hopefully that makes it a little bit more clear. So I think by now you should all be able to see all the paths. So hopefully that makes it more clear. So now you can all see all the paths. So this should be clear by now, hopefully. So is this clear to everybody how there are 6 ways from just listing them all out? Sure. Are there any questions on this part? So you can either ask or you can put in the chat. Let's go to the second way. So now here's the second way, the smarter way of doing it, which maybe we'll have time to go over. So let's say we have another grid, 2x2 grid. So let's say we have a 2x2 grid at the center here. Now I have to go from the top part. So this is a really easy way to do this. you have to take a right step, a right step, and then an up step. You have to take 2 right steps, 2 up steps. That's clear, right? But remember, in order for the shortest possible path, we cannot take any bottom or left steps. We can only take right or up. As you see in all the possible paths, a right step or an up step. So a right or an up step. Okay, so now we can really take, so in this case, we take a right step, then an up step, then an up step, then a right step. In this case, we take a right step, then an up step, then an up step. In this case, we take a right, an up, a right, and an up. In this case, we take a up, up, right, right. In this case, we take a up, right, right. In this, we take a right. Sorry, we don't take a right. We take it up, up, a right, and a up. So we see that in each of these cases, each of these grids, they correspond to an ordering of this word. So in any way we order these words, whenever we order these words, in any way we do it, we always get a valid path because we really just have to take some right steps and some up steps in some order that we don't know. And now it becomes, and now, yeah, we have to order all these letters somehow. So now how can we do this? Well, now as maybe you can just think of it as 4 slots. We have a R, and a U, and a U. So there's actually some ways using some choosing notation that I don't want to go into here. But you can think of them as 4 factorial ways to just arrange all the letters. And the reason for this is, as some of you, I don't think I want to go into that because I haven't talked about factorials here. But you can think of it as where can the R go? I'm not sure how. So there's four spaces. The R can go in the first spot, second spot, third spot, or fourth spot. So the first R can go in 4 places. Now the second R, so let's just say the R went here. So there's 4 choices for where the first R can go. Now the second R, and the second R can go in any of the other 3 places. It can go here, here, or here. But then we see that switching 2 R's is the same thing. We have 1 on the left, 1 on the right. It's the same as having, so there's no R1 or R2. It's just R1, R2. They're interchangeable. So it doesn't really matter whether we have the first R there or the second R there. So it's just going to be 6. And don't worry too much about this explanation. It's a little bit of a tricky concept. As long as you get the first method, and we can just, and yeah, another way, rather than listing all the paths, you could just write out all the permutations of RR, UU. And this is a more, so don't worry about, if you don't understand the second method, this is a more advanced method. It's more useful for other more advanced competitions, but you don't really need to know this. As long as you get this first method and listing out all the permutations of the letters, you should be good. So don't worry too much about the second part. Okay, so are there any questions on this method? Okay, then that's it for today. And I will send another video if you want to learn more about combinations, permutations, and some harder combinatorics topics. So if you're interested, if you found this a little bit easy or something, you can always watch that video. Okay, thank you for coming, everybody. See you all next class. Bye.